Hello and welcome back to Chemistry Talk. Today we'll be continuing our discussion of thermochemistry by talking about calorimetry. Now, so far we've talked about enthalpy and specific heat, and that is all combined when talking about calorimetry. So, what is a calorimeter? A calorimeter is a thermally isolated area of the universe where reactions can occur at standard conditions. So, with standard conditions, mean that when you're given a enthalpy or a heat and you see that little superscript there, that means standard conditions, which I'll abbreviate as SC here. So a calorimeter helps us attain those standard conditions. Now this is a coffee cup calorimeter I have here. It's a styrofoam cup. You have a thermometer in there, a stirrer, and an insulated cover. Now what you can do is add water or some kind of liquid in here, add a metal, calculate the heat of the metal in the water, and then solve for either the mass, the specific heat of the calorimeter, something. But you're often given a piece of metal and it's added to water in a calorimeter, and using the law of energy conservation, you can determine the mass. Now you can also solve for temperatures and heat capacities, but um, I'll show you examples of that. But typically, if you're using a styrofoam cup calorimeter in a high school or college lab, you won't be attaining perfect standard conditions or because it's not perfectly thermally isolated. But if you're in a high tech lab, these conditions can happen easily. So example one here, um, I have four examples. In a calorimetry experiment, a student dissolved 3 grams of urea in 50 grams of water. The initial temperature of water was 22 degrees Celsius, and the final temperature of the solution, keyword, was 19.1 degrees Celsius. If the specific heat capacity of the water is 4.184, what's the enthalpy change, or Q, in the surroundings for dissolving urea? Well, what is Q? Q is the heat, and it equals the mass times specific heat times delta T. So we're just solving for Q here, but be careful because you're solving for the heat of the solution, which has a mass of not 50 grams or 3 grams, of 53 grams for adding the urea and the water. So Q equals 53 grams times the specific heat of water, 4.184, times delta T, which would be the change in temperature, final minus initial, 19.1 minus 22 degrees Celsius. You get that to be negative 2.9. So when you do the multiplication, you get that the heat of the solution equals negative 643 joules. So it doesn't ask, but you could classify this reaction as exothermic because you have a negative value for Q. Means we're losing heat here. It's a net loss of heat. Okay, that was fun. Let's take it up a notch. An 11-gram sample of calcium chloride was dissolved in 125 grams of water, both substances at 25 C. Calculate the final temperature of the solution, assuming no heat loss, and the specific heat capacity of the solution and the water are the same at 4.184 joules. The enthalpy change is given for dissolving calcium chloride. Okay, this is interesting. We're given the enthalpy change for just dissolving calcium chloride, and that would be the dissolving of calcium chloride would be our system. Our surroundings are what we're solving for. That's the solution. The solution equals the surroundings. The heat of the system plus the heat of the surroundings using the law of energy conservation, has to equal 0. You know the heat of the system, so if you solve for the heat of the surroundings, which is the solution, you just flip the sign, you get positive 8,078 joules. So the easiest way now to get after the final temperature is to solve for delta T. So what do we know? We know Q is equal to the mass times the specific heat times delta T. If we manipulate that algebraically, delta T equals Q divided by mass times specific heat, and that equals delta T. So what is Q? Q is that positive 8,078 joules. What's the mass? Well, be careful. Once again, it's the calcium chloride plus the water. So 136 grams. And the specific heat, we're assuming no heat loss, so it would be the specific heat of the water, 4.184. And that equals delta T. So you do the math, delta T comes out to be 14.2 degrees centigrade. Is that our final answer? No, it is not. We're looking for the final temperature. That just gives us the change in temperature. So what does delta T actually equal? Delta T equals the final temperature, what we're getting after, minus the initial temperature. We know the delta T, 14.2 degrees centigrade. We're going after the final temperature, and we know the initial temperature is 25 degrees centigrade. Solve for final temperature, you add 25 to both sides. And you get the final temperature to be, quick math here, 39.2 degrees centigrade. And that is our final answer, the final temperature. You know that it's correct because the final temperature, 39.2, minus the initial 25 gives us the 14.2. Okay, that was good. Let's see another example. Calculate the specific heat of an unknown metal if 220 grams of it is heated to 98 degrees Celsius and dropped into 100 mils of water in a calorimeter. Both the water and the calorimeter are initially at 20 degrees Celsius, and the entire system reaches equilibrium at 24.5 degrees Celsius. So assume the heat capacity of the water is 4.184 and the heat capacity of the calorimeter is 10 calories. This is interesting. We haven't talked about heat of the calorimeter, but the heat of the calorimeter always equals Kc, the calorimeter constant, times delta T. So in these problems, I like to write out what I know. So I know I'm going to have 3 heats here. I have the heat of the metal, the heat of the water, and the heat of the calorimeter. I know that the metal is 220 grams. The water, we have 100 mils of it, so that's 100 grams. The density of water is 1. I know that the initial temperature of the metal is 98 degrees Celsius. The initial temperature of the water is 20 degrees Celsius, and the initial temperature of the calorimeter is the same, so they will have the same change in temperature. I know the final temperature of the metal and the entire system is 24.5 degrees Celsius, so that's for everything, the entire system. So delta T of the metal is going to be a negative value, negative 73.5 degrees Celsius, and the delta T of the water in the calorimeter is, fix this here, is 4.5 degrees Celsius. We're looking for the specific heat of the metal that we don't know. The specific heat of the water is 4.184. And the specific heat, or the calorimeter constant, Kc, is 10 calories. So what can we do here to solve for the specific heat of the metal? We know that the heat of the metal plus the heat of the water plus the heat of the calorimeter has to equal 0, law of energy conservation. So the logical thing to do would find the heat of the calorimeter and the water and then solve for the heat of the metal. The heat of the calorimeter, Kc, 10 calories, times delta T, 4.5. You get the heat of the calorimeter to be 45 calories. Heat of the water, mCp, specific heat, delta T. This is all just plugging in now. The mass of the water, 100 grams. Specific heat, 4.184. Delta T, same as the calorimeter, 4.5. So we get the heat of the water. Quick math, 1,882.8 joules. So we can solve for the heat of the metal now. The heat of the metal plus the heat of the water, 1,882.8 joules, plus the heat of the calorimeter, 45 cal, has to equal 0. And we get the heat of the metal to be negative 1,927.8 joules. Now I'm happy that this is negative because we have a negative delta T for the metal. So now let's solve for, let me change colors here. Now let's solve for the specific heat of the metal. The heat of the metal equals the mass times the specific heat times delta T. If you manipulate that for specific heat, you get the heat of the metal divided by the mass divided by delta T gives you specific heat. Mass heat of the metal, we just solved for, negative 1,927.8 joules. Mass of the metal, 220. Delta T of the metal, negative 73.5 degrees Celsius. So you get the specific heat of the metal to be 0.12 joules per gram degrees centigrade. And that is our final answer. So setting up this table ahead of time helped us solve in the end for the specific heat of the metal. All right, last problem. A calorimeter contains 120 grams of water at 20.4 C. 110 grams of additional water is added at 39.3 degrees Celsius, and they're poured in together and the contents are stirred. The entire system reaches equilibrium at 29.3. What's the heat capacity of the calorimeter? Interesting. I'm also telling you that the heat capacity of the water is 1 calorie, so it's no longer in joules. So this is interesting because instead of having a metal, some water, and a calorimeter, we actually have two waters. We have water A, water B, and the calorimeter. So let's plug in what we know. The mass of water A, 120 grams. The mass of water B, 110 grams. The initial temperature of water A, 20.4 degrees centigrade. Initial temperature of water B, 39.3 degrees centigrade. Initial temperature of the calorimeter, well, that would be the water that's in the calorimeter initially, so that's water A, 20.4 degrees centigrade. Final temperature of everything, system reaches equilibrium at 39.3 degrees centigrade. Sorry, that should be 29.3 degrees centigrade. So delta T of water A, (8.9). Delta T of water B and the calorimeter, -10 degrees Celsius. So that would be for the calorimeter and water B, and the delta T of water A is 8.9. So we know that the heat of water A plus the heat of water B plus the heat of the calorimeter equals 0. We know that the specific heat of our waters are both 1 calorie, but we're solving for the specific heat capacity of the calorimeter, the kcal, which we don't know. So let's find the heat of water A first. The heat of water A would equal mass times specific heat times delta T. Mass of water A, 120 grams. Specific heat, 1 calorie. Delta T of water A, 8.9. Heat equals 1,068 joules. So that's water A. Water B is going to have a negative heat because it has a negative delta T. mCp delta T. The mass, 110 grams. The specific heat, 1 calorie. The change in temperature, -10 degrees Celsius. Heat of the water B, -1,100 joules. So that is the heat of water B. So if you solve for the heat of the calorimeter, the two heats of the water plus the heat of the calorimeter have to equal 0. So the heat of the calorimeter equals 32 joules. 1068 plus negative 1100 gives negative 32 joules. Solve for qcal. You get 32 joules, but the heat of the calorimeter equals Kc delta T, and we're solving for the heat capacity of the calorimeter. So quick algebra, the heat of the calorimeter divided by delta T equals Kc, the heat capacity of the calorimeter. Heat of the calorimeter, 32 joules. Change in temperature, negative 10 degrees centigrade. Quick math, 32 divided by negative 10. You get the heat capacity of the calorimeter to be 3.2 calories per gram degrees centigrade. And that is the final answer. I hope this video helped you to understand calorimetry, and in some future videos we'll be continuing discussion of thermochemistry. Thank you for watching.